just putting that out there. All right, so guys have hopefully looked at my worksheets. I posted worksheet 16. Going over that. If you have any questions, stop me as usual. Today is just a lot of reactions. So we have this substrate and H2 over PtO2. What will the product be?
Just an alkene?
Alkene, or did you mean to say something else? Like we're starting with an alkene.
Alkane, I'm sorry.
Yeah, just making sure. So it just reduces the double bond to a single bond. And if you didn't go over this, it's not something you might have to worry about, but the hydrogens are attached cis to each other. And again, like if you didn't cover this, don't worry about it. And even if you did, it's not something you have to know, but the platinum O2 catalyst, or it could be PDC, a palladium catalyst. It's just like a sort of sheet of metal. You can think of it like that. And like the hydrogens are going to get attached from this metal catalyst, so they're going to attach from the same side. So because they're attached from the same side, that's why they're cis here. That's why it's in addition. But you could just draw this and you're more than likely going to be okay. Or like if you're just identifying products based on whatever the exam will be like, just both of these are valid is the point. Okay, so that's number one. Okay. So here we have NBS, H2O, and DMSO. DMSO is just a polar solvent, so don't really have to worry about it. It might be non-polar, but it's just a solvent. But the NBS and H2O are important. Do any of you remember what NBS purpose it serves?
Is the NBS bromide solvent?
Yeah, it's a source of bromide. That's correct. So it's a source of Br2 because it's easier to handle than Br2 by itself. So you could think of this as writing the arrow like this. Like it's going to be the exact same mechanism and reaction, and I'll show the mechanism. Even though you guys have seen it before, we'll just go over it. But it's just think of the NBS as giving Br2 and then just do the mechanism the same way you normally would, or draw the product the same way you normally would for this. So when adding Br2 and H2O, the first step looks like this, with a sort of cyclic intermediate forming between the alkene and the bromine, and then the other bromine bond breaking. And you have this positive charge kind of shared between all of the things in this free membered ring, the two carbons and the bromine. So now we also have water present, and it's going to attack what would be the more stable cation if a carbocation by itself were to form. So like this position on the left is secondary, that carbon is secondary, and then the one on the right is tertiary. So if a carbocation were to form, the tertiary one would be more stable. So that's where the water attacks, and then this bond breaks, so the octet isn't broken. And you can think of this water as attacking from the back to break these bonds with the bromine. So when that happens, this bromine's going to be on a dash, and the water is going to be on a wedge. So they have opposite stereochemistry. Water is positive, but that bromine ion that formed before can take the hydrogen. So a side product, thank you. A side product is hydrobromic acid, and you get the Markovnikov product for the alcohol. So this is Markovnikov for OH, and then it's anti-stereochemistry because the Br and the alcohol are trans to each other. And this mechanism shows why, and this is a mechanism that you should know. And there are a lot of other mechanisms that are similar to this. So if you know this one, then you can kind of extrapolate it to the other ones and remember more for less brain power, I guess. That's one way to put it. So moving on to C. We're reacting with MCPBA. CH2, CO2, that's dichloromethane, that's just a solvent. Does anybody know what the product is when we react an alkene with MCPBA?
Would you be creating an epoxide?
Yep, it forms an epoxide. And an epoxide is just a free membered ring with an oxygen in the middle. That's all it is. So you could draw it like this to show that it's SIM because it is SIM. Like they should both have the same stereochemistry, but I think you could draw it like this and you'd probably be okay. I recommend doing it like this to be safe if you end up drawing structures. I don't know what your test will be like, but this is technically more correct.
Just a quick question, man. For examples like that, the solvent and stuff, does that have, like, what does that do for the for our reaction?
Well, CH2Cl2 is dichloromethane. It's one of the most polar organic solvents because of the two chlorines. So, like, I don't know all the details of this reaction, but like, I'm assuming that you could also have some other kind of polar solvent here, but this is just a common solvent. I like to answer your question. Solvents are generally either polar, and if they're polar, we use this, or non-polar, and if it's a non-polar solvent, we use ether or THF. And ether is just diethyl ether, so that's this. And then THF is this. So they look very similar because they're both non-polar. I mean, I don't have an exact answer for you, like just in the past, chemists have probably found, oh, this works better in a polar solvent than it did in a non-polar, so they just use dichloromethane. And then like with HBr, the next reaction, it uses ether that works better in a non-polar solvent. It's something that they found by trial and error, but I don't know exactly if there's a reason that I can explain. So I kind of went all over the place, but that's partly because I'm not sure there's an answer for you.
No, it's all good. Thank you, man. Appreciate it.
Mm-hmm. So here was saying, we have HBr, and we could put ether or THF. They're both very similar, like I just showed. So I'm just going to put THF whenever I wrote ether on the worksheet. This is a reaction we've seen plenty of times. So first step is the alkene attacking hydrobromic acid, taking the proton. I'm doing this quickly because I've done it a lot in the past. The hydrogen attaches here because that is the secondary position, and this is the tertiary position, so that cation is more stable than the secondary one would be. And then the bromine ion will attack the cation. And you just get the Markovnikov bromine added. So that's that, something I've seen a lot. E is another one that I've looked at before, but I haven't done it as much. So just like before, like this is just a polar solvent. It probably just is conductive to the reaction going on. Sometimes the solvent, like in the case of Cl2 and water, the water is both the solvent and it's acting as a reagent. So it kind of depends on the reaction, like what role the solvent does. But here, it doesn't really do anything besides it's kind of just a medium. So we form this intermediate with the sort of ring with the chlorine. And then the other bond breaks and the other chlorine comes in, attacks that carbon from the back, breaks this bond. So this is going to be a dash, this is going to be a wedge. They're trans, it's anti, and there's no Markovnikov or anti-Markovnikov here because we just added two chlorines. It doesn't matter which one went where. All that matters is that they're trans to each other at the end. That's because of this cyclic intermediate with the cation in the middle and how the chlorine comes in. Okay, so on to F. Does anybody know what these conditions lead to? Can I draw the products down here? This is a bit of a weird one, I think. The mechanism for this is like the CH2I2 acts as a carbene. Besides knowing that this is a carbene reaction, you don't really have to know the mechanism, but it leads to a cyclopropane forming. So you could draw it like this, just like the epoxide with like the two wedges to show that the carbon that's attached was added with like cis stereochemistry. Or you could probably just do it like this. It's just a triangle forming where the double bond was. That's a cyclopropane. So CH2I2 over zinc copper and an ether solvent, that gives you a cyclopropane. And the name for this reaction is Simmons-Smith. So knowing the names of reactions might be important. He might ask you some multiple choice question like, what is the product of a Simmons-Smith reaction? And maybe it would say like epoxide, diol, cyclopropane, and something else. I don't know, I'm just coming up with stuff off the top of my head, but the answer would be cyclopropanes. Just like knowing what conditions lead to what products and what the names of those products are is important because he can ask word questions about giving you like these substrates, and you should be able to figure out what he's asking and what he wants. All right. So again, just putting THF where I wrote ether, they're both basically the same. And OH minus is just NaOH, but it's basically saying the same thing. So what do these conditions lead to? Does anybody know? Okay, I am guessing the answer is no. So I will go over it. Go ahead and move this, the product. It's kind of pushing it. I'll just erase it and redraw it. The product is enzyme-Markovnikov added alcohol. So this position on the top is tertiary and this is primary. So it adds to the less substituted spot, the primary one. That's where the alcohol goes. And the alcohol and hydrogen that get added are cis to each other with this reaction. I don't think you have to know all of the steps in the mechanism or even like any of it, but it kind of helps you remember why the product is what it is over here. So, sorry. So, an intermediate will look something like this. Because we added BH free. So, like, this is BH free down here. The BH2 is like one part, and then the H is also bonded to the borane still, and it's bonded to the alkene. It kind of forms this sort of square. And the borane is down here on the bottom because like BH2 is kind of large, just like a methane. It's something I've talked about in the past, like methyl groups are large and methyl groups don't want to get close to other methyl groups because they're steric strains. So it's the same kind of reasoning here. The borane is far away from this more substituted carbon to avoid steric strain. So the borane goes down here and then the hydrogen just kind of stays here. That's the first step with the BH free and the THF. And then the second step with the H2O2 and everything else is what basically just turns the BH2 into an alcohol. That looks pretty bad. And it's going to attach the alcohol in the same position that the BH2 is here. And you can see like the BH2 and the H are in the same direction. So that's why there's cis at the end. And that's why the alcohol gets added here. So it's enzyme-Markovnikov. And it's SEN addition. So those are the two notes on this reaction. That's something that is probably going to come up on a test, so it is good to know. If you're having trouble remembering reactions, flashcards help with like just testing your memory, but doing practice problems is the best thing to do because that'll cement what you remember. Right, so number 2 is just more reactions, but reactions of a specific type for the most part. Okay, so here we have a 2-step process. The first step has O3, which is ozone, and the second step has zinc and acid. Does anybody know what these conditions lead to?
Cleavage of some sort happens.
Yep, it cleaves the double bond. So we can look at it like this, kind of just draw a line for the double bond to show that that bond is going to break. So an easy way to do this is like draw both. Like if it's not a cycle, then there's going to be 2 products. So draw like the left side, and then where the double bonds to the carbon was, there's still going to be a double bond, but it forms a carbonyl instead of a double bond with a carbon. And then on the other side, we've also got a double bond to an oxygen. So this carbon here was bonded to a carbon here and a carbon here. That's why it formed a ketone, because it had substituents on it. And then this carbon here is bonded to a carbon here, but it's also bonded to a hydrogen. So there's still going to be that hydrogen there. And this is an aldehyde. So if there is a hydrogen on the double bond, or on at least one of the double bond carbons, then there's going to be an aldehyde formed. But if there's two substituents, it's going to form a ketone. And this is with the ozone cleavage of a double bond. It might lead to different products depending on the conditions we use, which we'll see in a bit. So moving on to B. Same conditions. So again, we're gonna cleave this bond. You replace the double bond to the carbon with a double bond to an oxygen, so we form a ketone with the ring over there. And then this carbon on the right is bonded to two hydrogens. So we're still gonna have a carbon bonded to two hydrogens, and then it forms a double bond with an oxygen. So this is again an aldehyde. And specifically, this is formaldehyde. So this alkene here is at the end of a chain, which is similar to like this or this, like they're all at the very end of a chain, so it's a terminal alkene. If it was within a chain like this, it would be an internal alkene. And I'm throwing around these terms because they probably came up with alkynes today, so it's good to be able to distinguish between internal and terminal. And like if we cleave a terminal alkene with ozone, you can see that leads to formaldehyde. So I don't know, maybe you could make a true or false question out of it. Cleavage of an internal alkene with ozone will form formaldehyde as a product. It's a possibility. It's a question I was able to come up with, so could he. So I'm just throwing it out there. Do you guys know what these conditions lead to with an alkene? Okay, they're also going to cleave the double bond. So it's going to be similar to the ozone reaction, but not exactly the same. So they're saying cleave the double bond, so you can draw the line through it like this. And just like before, if there's a substituent on the carbon at the double bond, like there's a carbon here and a carbon here, there's no hydrogens, it's just going to form a ketone. Nothing special happens. But like for the other side, there's a hydrogen here, so it's going to form a double bond to an oxygen like before. But instead of forming an aldehyde where the hydrogen was, like the hydrogen is going to get oxidized and you're going to form an alcohol where the hydrogen was. So overall, you get a carboxylic acid. So KMNO4 is a strong oxidizing agent, so it oxidizes this hydrogen to form a carboxylic acid. And I'm throwing that term of oxidizing agent with KMNO4 out because it's going to come up again and again over the next year. So you don't necessarily have to know that now, but it's better to see it earlier than later. Just know that KMNO4 and acid will cleave a double bond. It's going to form a ketone in the same positions that the ozone formed a ketone, but it forms a carboxylic acid where an aldehyde would have formed with ozone. So just be aware of that distinction. And I'm not getting stopped, so hopefully that is clear. So same conditions, it's going to cleave the double bond. You get a ketone for this right side of the double bond because there's a substituent here and a substituent here. There's no hydrogens. And then for the left side, there are 2 hydrogens. So obviously you're going to get at least 1 carbonyl because we always do. And that is, that's just replacing this double bond with the other carbon in the alkene. You can think of it like that. But then, like, if we just had this, well, I suppose, like, you might think this would form, but it doesn't, because honestly, I can't really explain exactly why, but you can just remember that KMNO4 is a strong oxidizing agent, and it basically just like completely oxidizes this terminal carbon here. So it forms 2 carbonyl bonds, and this is just carbon dioxide. So just like I was saying with the terminal alkenes and ozone cleavage, that led to formaldehyde. So you might ask, what does cleavage of a terminal alkene with KMNO4 lead to? And you can say carbon dioxide, because that's what forms here. So yeah, I'm sorry, I don't have an exact reason for why that forms, but it's just, I guess it's something that you have to remember because I can't explain it. Right. So this substrate here with the alcohols here, there's a term for it. Does anybody know what it's called? Like we had the epoxide with that sort of free-membered ring, we have cyclopropanes. There's a term for this substrate here. Okay, I'm guessing you're looking for your notes or you're just not sure, so I'll just go ahead and give it. You can, obviously if you were naming this, you wouldn't number it like this, but the distance between these 2 alcohols is like 1, they're right next to each other, so it is a 1,2 diol. It's a diol because there's 2 alcohols, that's where the ol comes from, and 1,2 because they're right next to each other. So knowing that this is a 1,2 diol is just like another sort of name that you should know. Okay, so that's a sort of nomenclature aside. I'm going to assume that since you guys didn't remember the name for this, you don't know what these conditions lead to, and that's okay because you just learned it on Tuesday and you might not have had time to practice, but you have a week to practice. So just recognize that like when you have a 1,2 diol, when you have a 1,2 diol and you have these conditions, HiO4 and water, it's going to cleave the double bond. not the double bond, it's going to cleave the bond between the two alcohols. So it's going to cleave this bond like this. And it's going to cleave it in the same way that we cleaved, like, that cleavage occurs with ozone and zinc acid, like those two steps. So it's going to form these two products, and hopefully you recognize that this is the exact same set of products that we got from part B with this reagent being cleaved by ozone. So it forms ketones in the same position that the other two cleavage ways form ketones, and it forms aldehydes just like ozone does. It doesn't oxidize things. But instead of there being a double bond, there's two alcohols, and it just cleaves the bonds between the two. So that's this set of reagents. All right. Again, THF is the same as ether, pretty much. Okay, so can anybody tell me what this set of conditions will lead to? It's something we've seen earlier today.
It's the anti-Markovnikov with the syn addition, yeah.
Mm-hmm. So alcohol gets attached to the anti-Markovnikov position, which, if we look at these two, this is tertiary, this is secondary, so it's going to get added here. And it's going to be cis to the hydrogen that gets added. So they're both going to be wedges or both dashes. It doesn't matter, they just have to be the same. So that's that. I'm just going to erase this to save myself a bit of time. Yes, I'll erase that too. Do you guys know what this set of conditions leads to? It's not something I went over today, but it is something that needs to be known. So it's very similar to the last part, part F. I'll go ahead and do the mechanism or sort of summary of the mechanism to show you guys why it is what it is. So there's some electron pushing that goes on. It's kind of similar to what happens when you add Br2, because like you can see that this intermediate looks very similar to if we added Br2 to an alkene, you get like the Br with the sort of free-membered ring and the cation in the middle. These two look very similar. And just like if we were adding Br2 and H2O, the OH would attack here, the more substituted spot, because that would be the more stable cation if it were to form. The same thing happens here with this mercury and this sort of free-membered ring. We have water, and the water comes in and breaks this bond. So now this will be a wedge. And when the water gets added, it's going to be positive, but when this thing here forms, we also form an acetate ion, so it just ends up taking a proton from the water. I'm skipping that step, but it ends up taking the proton and just getting protonated like that. I'm just trying to save space and a bit of time. So we end up with the alcohol like this, and that is all step 1. And then step 2, when we add the NaBH4, I'll just move this quickly. When we add the NaBH4, I'm just putting 2 to show that's when that comes in. That basically just replaces the mercury acetate with a hydrogen. You don't really have to know how that happens, just know. Well, you don't even have to know like this series of steps, but it helps explain why the product is what it is. So it's easier to remember. So you have the alcohol attached to the Markovnikov position, which again, like tertiary versus secondary, going to the tertiary spot. And then the alcohol and hydrogen are added trans to each other. So it's anti-addition and it's Markovnikov. Those are the 2 notes on this. And hopefully you guys are noticing the patterns that I'm pointing out. Just like there's a lot of parallels in mechanisms, so you don't have to remember each individual mechanism. If you remember one, you can remember others that are similar, so it cuts down on memorization. Moving on to number 3, more reactions. So I'm giving you the single substrate and a bunch of conditions and just showing how different conditions lead to different things. Does anybody know what this set of conditions leads to? OSO4 in the first step, and then the second step, this stuff in water. Well, that is okay. I'll go over it if nobody knows. So this is going to lead to a 1,2 diol, and specifically it's going to lead to a cis 1,2 diol. So these conditions lead to a cis 1,2 diol. And the cis is important because there's another way to form diols, and it forms trans diols, and we'll get to that when we get there. But like the stereochemistry of the diol is important to distinguish. And you can kind of remember how this happens by, I mean, I really only know one picture that sort of helps remember this, but like an intermediate that forms looks something like this. The 2 oxygens, because of how the osmium sort of binds with the alkene, like they're facing towards the same direction. And that's the first step. And then the second step, you add this stuff, and there's probably an osmium byproduct, but it just ends up turning those oxygen bonds to alcohols. And because they were cis before, they're going to be cis now. I guess I'll just make them wedges since I have them as wedges in my product. But yeah, that's a very simplified mechanism, and that's all I know, so I can't really tell you the details. But if you remember this picture with the osmium, maybe that'll help you remember that it's cis at the end and it forms a diol. And if that doesn't help, just practicing also is a good thing to do to just remember things. because you can remember by repetition. So another set of conditions. What will this lead to? H2 over PTO2.
An alkane, yeah.
Thank you, George. It just leads to an alkane. You can specify the stereochemistry. It's cis, or you could just draw the alkane. Either works fine. Just gonna keep the substrate there and erase all this. Now we have Br2 and CH2Cl2. What is this going to lead to? The CH2Cl2 is just a solvent. It's not super important, but the Br2 is. So we're just adding two BRs. I can go over the mechanism if you want me to, but it's very similar to stuff I've shown multiple times today. So unless you want me to, I'm just going to show you the product. So the two BRs get added and they're trans to each other. That's something we've seen multiple times before. Putting THF instead of ether, again, same kind of thing. So what do these conditions lead to? We have our skeleton here. So something I went over earlier today, when you have CH2 and I2 as the reagent over zinc copper and an ether solvent, that will lead to a cyclopropane. So you can draw it like this, or you can draw it like this, whatever works. They're both pretty much the same. So that's that. It's just something the practice will help with. I know I'm saying that a lot. I'm probably going to keep saying it because practice is really all that's going to help you with this class. And then the last part here, Cl2 and H2O. Can anybody tell me what the product for this is going to be?
Is it the alcohol in the Markovnikov product?
Yeah, we have.
Tertiary.
Yeah, the alcohol attaches to the Markovnikov spot, and then what else?
And then the chlorine attaches to the first position of the.
What about stereochemistry?
They should be cis and trans, or trans.
Yeah, they're trans. There you go. So if you just do what I had before without indicating stereochemistry, I'm sure you'd get partial credit, but the trans stereochemistry is important, so you should specify that. That's why I kept prodding you. So it's just important. And that is number 3. So moving on to number 4. So for this first one, we have an alcohol, and there is a set of conditions we can use to go from an alcohol and form a double bond. Do any of you happen to remember that? It's okay if you don't, just make a note of it being something you need to remember if you don't. Okay, I'm guessing the answer is no, since that's not quite correct. Okay, so we have H2SO4, which could probably also be H3O+. It's just some strong acid. And we have an ether solvent. And 50 degrees Celsius is like standard for this, I guess, but it could also just be written as heat or delta. Delta means heating. So H2SO4 and heating with an alcohol is what leads to a double bond like this. So that's that first step for number 4. And now, what set of conditions leads to this alcohol here from this double bond? Can anybody tell me that? There's a couple ways we can add an alcohol to a double bond. And we've gone over most of them today. So this double bond here, we have this carbon up here and this carbon down here that the oxygen can attach to, and it wants to attach to the bottom. This is tertiary for the carbon. This is secondary. So we're attaching the alcohol to the secondary position instead of the tertiary position. That means we're forming the anti-Markovnikov product. That's important because there's 2 ways to form an alcohol, but one of them forms anti-Markovnikov and one of them forms a Markovnikov alcohol. So to form an anti-Markovnikov alcohol, you have to do hydroboration, and yeah, that's the reaction, hydroboration, and then just forming the alcohol. So it's like this. You have BH3 and then H2O2, OH minus, and water. That leads to the anti-Markovnikov alcohol. So yeah, that is something that's good to know. And the second part of number 4. Here is the other way that you guys have learned how to make double bonds. This is starting with a halogen instead of an alcohol. Does anybody know how to get from the halogen to the double bond? Okay. It uses a base. I'm butchering these OHs. Okay, it is KOH, or it could be NaOH, or it could just be OH minus. It doesn't really matter. It's just some base, and then ethanol is just an alcohol. It might be ethanol, it might be methanol, but just like a base over some alcohol. But I think the base is the most important part. So base on the top with a halogen leads to a double bond. That is one of the 2 ways to synthesize an alkene. The other way is with the acid and the alcohol, like I went over in the last part. I'd recommend knowing both of them because they might come up. And then to get from this double bond to this product, what do we have to do? What set of reagents do we use?
Palladium would be one.
Yeah. At least I'm assuming you had the full picture. We use H2 and the palladium catalyst. If you just put H2 by itself and you didn't put the palladium, that wouldn't be entirely correct because H2 by itself probably isn't going to react with this. If it did, there'd be a lot of reactions like that going on. So you would need to put the catalyst. So that's just something to remember. Sometimes this thing on the bottom you have to put or it won't happen. But sometimes like the ether solvent, you don't really have to specify. It's just good to put if you remember it. Okay. So this is something I think I fixed in the final version of the worksheet I uploaded, but if you looked at it right when I uploaded it, you might have a different substrate. Just know that this was a chlorine. At first, it was supposed to be an alcohol, so fix that if he happens to get it super early. And E2OH is the same as ethanol. Oh, I gave it away. Okay, never mind. I'll just, that was what I was trying to go towards asking, but I just gave it. So that's okay. So this is another way to form an epoxide. We talked about one way to form an epoxide earlier. That was like starting from a double bond, use MCPBA and CH2Cl2, and that would lead to an epoxide. But this also leads to an epoxide, so you have an alcohol and a chlorine, and you react it with a base and ethanol, and that leads to the epoxide. You don't have to know this mechanism right now, pretty sure, but it'll come up in the future, so I'm going to show it to you now, so it might help you remember why this happens, and you'll get exposure to it for later. So the alcohol can act as an acid, and KOH is a strong base. So it takes a proton from the alcohol and gives electrons to that oxygen. So now the oxygen has a negative charge. Things with negative charges generally act as nucleophiles. That's something we know. And then this carbon bonded to the halogen, there's a dipole. So the carbon is electron positive, or it has a partial positive charge, so it can act as an electrophile. So this reaction can happen if the oxygen is the nucleophile and that carbon is the electrophile. And then the bond of the chlorine breaks. And then that oxygen here is now bonded to this carbon and this carbon, so it leads to this ring here, ring membered ring with it bonded to two carbons. And chlorine ion floating around, so that's byproduct. So there's two ways to form an epoxide. Now you've seen both. And here we have a 1,2 diol, and specifically this alcohol and this alcohol are trans to each other. So this is a trans 1,2 diol. You guys might remember I was talking about the cis diol being formed with OSO4 earlier, but this is trans. So there's a set of reagents that we can use to form the trans diol from this epoxide. Can any of you tell me what that is? That's okay. It is just going to be H3O plus, and I can show why with a mechanism. And you can like take a screenshot of this or look at the video I'm going to post later, but I'm going to erase the board to show how we get from this second step to the third product there. Okay, so we have this epoxide here, and we're reacting it with H3O+. So the first step, the epoxide, the oxygen here has lone pairs on it. And the acid's kind of floating around, leaves its proton out for the oxygen. So we form an intermediate. You don't have to know this mechanism, pretty sure, but it's very similar to other things you've seen, as you'll see in a minute, so hopefully you can remember it. So the oxygen is positive, but instead of putting the positive charge there, we could theoretically also put it like within the ring. And this might look similar to like this, or that could be a Cl, or it could be the mercury with the acetate bonded to it. Like, this is the third different set of conditions that we've seen where we have a free-membered ring and a positive charge in the middle. And when we had Br like this, you will hopefully recall that like when we were adding Br2 and H2O, the water would attack Markov-Makov position and break that bond. And that led to a trans product. So the alcohol and the bromine are trans to each other. And that trans stereochemistry is relevant here too, because we're going to have that water that formed when this happened come in and break this bond. So now this will be here. And to be honest with you, I'm not entirely sure where the proton goes. It probably goes to a different acid catalyst, but the water that gets added gets deprotonated, and because of how this electron pushing happens here, these two are trans to each other. That's on a dash, this is on a wedge. So it's trans. And like I've said, hopefully you recognize the similarity between this intermediate here and this intermediate here. It's like the same exact pattern. So you don't have to remember too much if you can recognize these patterns. So yeah, that's number 4. Moving on to number 5. So we're starting, or we're being given like a set of conditions. Here we have H2 and PTO2 and the product, and I'm just asking what substrate you could use to get there. So H2 and PTO2, that is just hydrogenation that adds protons to its double bond and just turns it into an alkane like we have over here. So there's a lot of different things you could draw for this. You could draw that. I kind of butchered that. You could draw this. You could draw that. You could put the double bond anywhere and they'd all lead to this because it doesn't really matter when you're just adding hydrogens. So there were a lot of answers to this question. Hopefully that one wasn't too bad. For part B, so we're using oxymercuration and demercuration. do you guys remember if that, like this set of conditions leads to the Markovnikov or anti-Markovnikov alcohol?
I think I remember it leads to the non-Markovnikov, but we have in this example they're both, or they're all secondary, so it doesn't really matter, right?
Well, two things. It actually leads to the Markovnikov. So the anti-Markovnikov is, I'm gonna erase this. It's okay to make mistakes. Like that's how you learn the most. So it's good to speak up, but this is how you'd get the anti-Markovnikov product with the BH free in the first step and then H2O2 and OH minus in the second step. So that's one thing. That is how we get anti-Markovnikov. So we're forming the Markovnikov alcohol here. That's like the first thing to recognize when you're given these sets of conditions. And then the second thing is like, this is secondary, this is secondary, this is secondary. But this at the end is primary, and this at the end is primary. So like, if we put a double bond here, both of the positions are secondary, so there's no regioselectivity. It would probably just form an equal mixture of both. You generally want to avoid forming a mixture of products, so you wouldn't want to use this. But if we put the double bond here, then this is secondary versus this being primary. And like I said, this is going to form the Markovnikov product. So it's going to put that alcohol only here on the secondary position, which is where we want it. So this is the substrate you would use with this set of conditions to get that product. Hopefully that makes sense.
Yep, got you. For some reason in my head, I kept thinking that Markovnikov only was like, I guess, exclusive to tertiary, but if it's down to primary or secondary, secondary is still considered a Markovnikov product, yes?
Yeah, it's the more substituted position. That's what's important. It's just easier to show off tertiary spots, but secondary versus primary is just as valid. So I'm glad you've recognized that. And also recognizing the regioselectivity for different reactions. Like I said, like the BH3 versus the mercury reaction, that's important. So here, I'm just going to go ahead and number the carbon. So between what two carbons should a double bond go if we're doing this set of conditions to form that product? So we have a bromine on carbon 2 and a bromine on carbon 3. So if we're adding two bromines, the bromines are going to go on both ends of the double bond. So it's just going to go here between carbon 2 and carbon 3. So this one hopefully isn't too bad. I maybe could have worded this question a little better, but hopefully you guys can see what I was looking for now as I go over it. If it wasn't clear at the beginning, the professor is probably better at writing questions than me, so it'll be more clear then. But that was number 5. Okay, I have 10 minutes, okay. So for number 6, I'm asking to show 2 ways that we can get like some substrate to this product I've shown. So there are 2 ways to form alcohols, or technically 3, but Just number days, like I have in the past. No, carbon 6 is at the end, but it's not super important. So what is one way we could form this alcohol? First, it's important to say where the double bond is, and then we can figure out what set of conditions we can use. So let's say we have the double bond here between carbon 1 and carbon 2. And then we want the alcohol to go to carbon number 2. So we're looking at carbon 1, which is primary, versus carbon 2, which is secondary. So what set of conditions can we use to get the alcohol to go to carbon number 2? It came up pretty recently in the last question. Let's see, oxymercuration and demercuration. Because that leads to Markovnikov addition of the alcohol, and the Markovnikov favors the more substituted spots at a secondary. That's why it goes to carbon 2. You could also so we can also do this, put the double bond between carbon 2 and carbon 3. And now carbon 2 is again secondary, carbon 3 is tertiary. So we still want the alcohol to go to carbon number 2. And now the carbon 2 is the less substituted spot because it's secondary versus tertiary. So we want the anti-Markovnikov product. And in order to get that, you have to use BH3, like I pointed out in the last problem. So BH3 and then H2O2, OH minus, and water give you the anti-Markovnikov alcohol. So this is two ways that we could get this product. And something I haven't really said today, but is important, is like, don't write this like this, because like the numbers there are important. If you don't put the numbers, you're basically saying you added all of this and all of this into the same beaker or flask or whatever at the same time, and that probably wouldn't lead to what you want. But when you put the arrows, you're saying, like, first I added the BH3 and the THF, and I let that react and form a product. And then once that was done, I added this. So they're two separate steps. And that is important. So if you see a reaction written with numbers like this on the slides or in the book, that's how it should be written. Don't neglect to put the numbers, or it will be wrong. Okay. So there's really only one substrate we can have starting with this, because it's a symmetric molecule, so it doesn't matter where I put the double bonds, but I'm putting it in the same position as where these carbons are with the oxygen. There are two ways we can form an epoxide. Can anybody tell me what one of them is? This is the easy.
One of them is.
It's what?
Sorry, I was trying to say one of them is the osmium tetraoxide.
So that condition will lead to, it's a two-step thing. Second step is like this. That's going to lead to a cis diol, actually. So like it does add oxygen, so they're similar in that regard, but it's not the exact conditions we're looking for. It's a good guess though, because oxygen being added like it's easy to mistake which ones add the oxygen in the way to form an epoxide. And these sets of conditions aren't exactly obvious for how to form an epoxide, but one of them that forms it in a single step is MCPBA with CH2Cl2. The solvent's not super important, but the MCPBA is what you absolutely should know. That will form an epoxide with a double bond. And then the second way is with the same substrate over here. It takes 2 steps. The first step, you add the Cl2 and water, so you're doing hydrohalogenation. And then the second step adds a base and ethanol. So after that first step, you end up with Cl and OH, and then that second step with the base is what does that reaction. I showed you guys the mechanism, like it ends up forming this ion and then it attacks the carbon and leads to that product. So it takes 2 steps. The first step goes from this to this product of the halogen and the alcohol, and then the second step forms the epoxide. So those are both ways to form an epoxide. They're both equally valid. If you were asked to get from this to an epoxide, you could put both of these and you'd be correct either way. So point is, like, there's a lot of the time multiple right answers to questions. And generally you want to take the path that takes the least amount of steps, but they're both correct. Okay, so here, again, like, we can really only have one substrate because it's symmetric, so it doesn't matter where the double bond goes, but I'm putting it here. And you can see that, like, there was a double bond here, but it's been broken, so we cleaved the molecule. Do any of you remember how to cleave a double bond? There's a couple ways we can do this. What's important to note too is we have the hydrogens here still, so we have aldehydes and not carboxylic acids. So if you want to cleave a double bond and form an aldehyde and not a carboxylic acid, you don't want to oxidize it. You're going to use ozone and zinc with acid catalyst, so that will cleave the double bond and form aldehydes there. That's one way to do this. And then another way we can cleave this, well, it's going to take more steps, but what leads to the aldehydes like this, we can form a diol. So in order to form a diol, this is actually something that was brought up in the last question. We can use the osmium tetraoxide reaction. That forms a cis diol like I showed before. And then, well, there's other ways to form diols and all of them are equally valid, but this is just what I'm going with. So if you decide to make a cis diol or a diol some other way, then that would work too, but this is what I'm going with. And then once you have the diol, these conditions with HiO4 and water cleave the double bond, the bond between the two alcohols, and they lead to that product. So this takes 3 steps to get there, but it leads to the same product. Okay. That's my worksheet. I recommend flashcards for getting used to these products. I mean, these reactions, and like, I have that wheel of reactions I posted. You can use that to practice, to check your work. and such, because that shows both the stereochemistry and the like Markovnikov and anti-Markovnikov. I don't explicitly say it, but I like if you look at the products, you can see it there. So that'll help you check your work. You're welcome. I'm also probably going to do a review session. I just wanted to ask for those of you who are still there, are you okay with me doing it over spring break? Probably the same time as I'm doing these workshop sessions. Okay, thank you for letting me know. I know it's not ideal because you'll be on break, but Tuesday is your exam. I can't do another workshop session. Monday would be difficult for me, and tomorrow is just too soon. So I'll send an email out about the exact day, but it'll probably be next week. I'll just try to review everything that I think will be on the test. So yeah, thank you for coming. Hopefully this was helpful, and good luck studying.